Well, before we do some extra work on equivalence relations, it's worthwhile reflecting on proof writing skills and some of the processes of different types of proofs. We can look at a direct proof. What does a direct proof mean? Well, here's an implication. If n is even, then n squared must be even. That's what we have to prove. If n is even, we can directly say that n is some multiple of 2, where k is an integer. And then we can say, if that's n, then n squared is 2k squared, which is 4k squared, which is even, since 4k squared is 2 times 2k squared. Hence, n squared is even. Now, in writing a proof, sometimes we're tempted just to stop here because we can feel that we've done it. We've done it and we feel good about that. But you should always write a closing statement. It might be a good idea to write QED at the end when you've done that, as a mental reminder that you have to show what was to be shown. Quo erat demonstratum means which was to be shown. We wanted to show that if n is even, then n squared is even, and now we've shown. That's a direct proof. Look at this one. If n squared is even, then n is even. We could try a direct proof here. We could say, just like before, if n squared is even, then n squared is 2k. And then we think, what does that mean? It means n times n is 2k. It's not quite so obvious how to proceed until you remember, since n can be written as a product of primes. Every integer can be written as a product of primes. Then 2 must be a factor of n. Hence, n is even. Not quite so obvious, but it's true. Now, I'm showing you this because you may not be satisfied with that as a direct proof. So there's another strategy. Indirect proof, using something called the contrapositive. Contrapositive means if we want to show P implies Q, in other words, if P then Q, it's logically equivalent to not Q implies not P. So we can say, let's assume if n is odd, then n is 2k plus 1, for k is an integer. I should have said in this one that n is an integer as well. Then n squared is 2k plus 1 squared, which is 4k squared plus 4k plus 1, which is 4k k plus 1 plus 1. This has actually turned it into a direct proof by kind of going backwards. Hence, n squared is odd. So what have we proven? We have proven if n is odd, then n squared is odd. Well, we started with if n squared is even, okay, that's our p, then n is even, that's our q. That's what we wanted to prove. What have we proven? We've proven not q is the opposite of q. And we've started with not q, and we've established that not p. Hence, if n squared is even, then n is even. QED. You might like that more than the previous one. Now that's an indirect proof using the contrapositive. That's not to be confused with the next one, which is another clever trick. Proof by contradiction. So here we want to prove the sum of a rational number and an irrational number is irrational. Now this is not an implication like the previous one that said if p then q. This is just a statement. The sum of a rational number and an irrational number is irrational. So we can say we will prove that if A is in Q, rational, B is not in Q, that means irrational, then A plus B equals C, where C is not in Q. So we add a rational with an irrational, and we get an irrational. So here's how we do the proof. We say, assume that this answer, C, right here, is rational. Let's assume that's true. What do we have? We have A plus B equals C. In other words, B is C minus A. Let's think about that. C and A are rational numbers because this is our assumption and this is our premise. They're rational numbers. Therefore, B is, if I write it as rational numbers, we can always write a rational number as a fraction, a quotient of integers, such that the denominators are non-zero. That means B is Pn minus nq over Qn. And that is a rational number, since Q and N are non-zero. So we proved B is a rational number. But that has contradicted our initial assumption. And something in maths can't be true and false. That's inconsistent. The only option is that our assumption here must be false. This is the process of proof by contradiction. Hence, C must not be a rational number. So that's the final process. You begin with something you want to prove. want to prove this statement. And you make an assumption of the contrary. Instead of C being irrational, we assume, let's see what happens if it is rational. And we derive a contradiction. In some textbooks they put a sign like this to signify this is a contradiction of what we assumed at the beginning. And that establishes that our assumption must have been wrong. Therefore C is irrational. Well, these are three processes we'll be using as we reflect on the process of proving something.